but we'll go ahead and start. So your lab this weekend is titled Isomers and Nomenclature Activity. And this lab is pretty much talking about the different types of isomers. So pretty much the purpose is stated in the beginning in blue, that you be studying constitutional and stereoisomers. And so I'm going to go briefly over what isomers are, and then, well, Crystal, if you have any questions, feel free to text it to me, and I should be able to see your text or your message. Essentially, isomers are molecules that have the same molecular formula, but they are connected or arranged differently to provide different names in some cases, different physical properties, and they will have similar chemical properties, but sometimes slightly different properties because one may be more stable than the other. But overall, they have different physical properties, different chemical properties, and different names. But they're made up of the same number of elements and types of elements. So if you were to write out the formula will have the same elements, same element amount, but when you actually connect the atoms to form the compound, they will be different. So to jump right into it, we're looking at, let's see, the first one here is constitutional isomers. With constitutional isomers, what makes them different? So going back to the chapter you're in right now, chapter 10, that has to do with alkanes. So I try to stick with alkane examples when I was writing this lab, the handout. So in your first example here, you're given constitutional isomers. These isomers, when you look at what they're made up of, essentially have 1, 2, 3, 4, 5 carbons, and then with the 5 carbons, you have 12 hydrogens. So you have 5 carbons and 12 hydrogens shown to you in 3 different formulas. 3 different structural formulas. So they have this, the main formula is the same, the main molecular formula is the same, having 5 carbons and 12 hydrogens, but the way they're connected are very different. So focusing on the longest chain, and it says here the longest continuous chain. The first structure has got carbons, all the 5 carbons in series. So carbon after carbon after carbon after carbon after carbon. And this would be a regular pentane, having 5 carbons in series. The next one has 4 carbons in series, making the longest chain. Then the 5th carbon is on the side. And then down here we have 3 carbons in series. And then the 4th and the 5th carbons are connected as side chains. So having a different number of carbons in your longest chain produces different isomers. As long as when you count the number of carbons and number of hydrogens, they're the same. Okay. And then when we look at B here, it shows you that sometimes you may have a functional group. And in this chapter, you should have learned what a functional group is. The functional group tends to be a group of atoms that are heteroatoms. So these atoms will be non-carbon, non-hydrogen atoms, and they're grouped together in that organic compound. And they're special because most of the chemical reactions will take place where your functional groups are. So the functional groups can have a group of atoms that are different from carbon and hydrogen, or they will have multiple bonds. So when you have double bonds or triple bonds, those are also considered functional groups. So sometimes functional groups are heteroatoms, atoms that are different from carbon or hydrogen, or they are multiple bonds. So double or triple bonds. So in this example you have right here, we see 3 carbons in series and a bromine in the end. That makes one formula. So the basic molecular formula has 3 carbons. It has 7 hydrogens and 1 bromine. Same thing with this formula on the right, but the bromine is connected to different carbons. On the left, it's connected to the carbon, the first carbon. Usually the carbon that you arrive to when you're going either from the left or to the right, or from the left to the right or the right to the left, is considered the first carbon. So this bromine is attached to carbon 1 from the right, but this bromine right here in the second structure is connected to carbon 2. So that makes these different compounds, and they even have different names, okay? And then see here, we're seeing isomers that actually where you have a different arrangement, once again, of the atoms producing a completely different functional group. In the first structure here to the left, we have 3 carbons, 6 hydrogens, and 1 oxygen. So the arrangement of the atoms produce this functional group. That's the aldehyde functional group. How do I know that? The name, the systematic name, ends with Al. On the right, we have a same number of carbons, same number of hydrogen, same number of oxygen, but this time the functional group produced is the ketone functional group. How do I know that? The name ends with ONE. So you will be learning how to name these functional groups down the road. And so you will get better at this or more familiar with it. And then, this is not in the right place, but let's move this down. Down here, we have what is called stereoisomers. Stereoisomers are different from structural isomers or constitutional isomers. Constitutional isomers, you pretty much, the difference is more obvious. It's not subtle. You can tell there's a difference in the structure. It's more obvious. You can see that these are 3 different structures, right? And even with the second one here, you can tell the bromine is in a very different place, so connected to a different carbon, which kind of alters the surface area of the whole molecule. With this one, once again, you can tell that this carbon double bond oxygen called the carbonyl group. This one's on the end. This one right here is in the middle. So the difference here is more obvious. In the stereoisomers, where you have 2 major types, one is diastereomer, the other one is enantiomer, the difference is a little bit more subtle. With diastereomer, the differences are more have to do with either the hydrogen positions or the heteroatom positions. Now remember, heteroatom is a non-hydrogen, non-carbon atom. So anything that's not hydrogen or carbon is called heteroatom. So that's the other atom. So in this case, in this first image right here, the chlorines are on different sides. So when they're on different sides of the carbon-carbon bond, they're considered to be on opposite ends, and this will sometimes be called trans. When the chlorines are on the same side, this is cis. But in this case here, these actually end up being the same structure because the single bond does not restrict the atoms from moving around. So the atoms that are here in the single bond can freely move around. So the single bond actually allows the carbon here to freely move around to give you this structure. So the structure on the right flips over to form the structure on the left when this chlorine flips up, and vice versa. When this chlorine flips down, you get the structure on the right. So the right and the left can flip to form each other. But in the double bond, that's very different. When you have double bonds, remember your previous lab, you learned that when you have a double bond, the double bond restricts the rotation of these other groups right here because this carbon cannot rotate around. So what that does is it forces this chlorine that's up here to remain in that position relative to this chlorine down here. It's a little harder for me to talk about this on computer. In class, I'm kind of in the zone here. It's a little harder, but I'll keep trying my best. Okay, so when you've heard of trans fats, right? And trans fats are bad for you. Well, the opposite of trans fat will be cis fat. But companies do not advertise cis fats as cis fats. If they did that, the consumers would not be so excited about it. They most likely won't buy products that have cis fats. So they just say no trans fat, okay? So right here we have the trans fat, we have the cis fat. Trans fat is opposite to cis fat, as in your chlorine groups are on opposite ends. In this case, a trans molecule. And this one here, the chlorine groups on the same end. And so trans just means the large groups, the non-hydrogen groups are on the opposite end. Or you can focus on the hydrogen groups. They're also on the opposite end of the carbon-carbon double bond. And over here, we have the carbon-carbon double bond where the hydrogen groups are on the same side, or the chlorine groups are on the same side. So this is cis, same side, like waving your hand, same side. And then trans, which is the opposite, like that. Okay, so it's kind of like a dance. Cis, trans, okay? I thought I kind of break the tension by including this little cartoon picture that I saw where apparently the witch from Hansel and Gretel somehow went to a diet seminar. So remember in the story of Hansel and Gretel, the witch has a house that's made up of all these cookies and candy and stuff, and she uses that to lure kids into her house. But she's become health conscious, not health conscious enough to not eat the kids, but health conscious enough to not feed them sugar right before she eats them. So she is luring them over, but all her candy is now sugar free and fat free, and there is no cholesterol. I'm surprised Hansel and Gretel still went there. Maybe they can't read, I don't know, but I don't know how tasty this candy will be. So back to the structures. Now that we've seen how this looks in organic chemistry, we're now taking a detour and applying that in biochemistry. So this is an example of the trans fat we're talking about. Actually, this right here will be a regular. Cis and trans, by the way, only occur when you have a double bond or you have a cyclic compound. This is not cyclic. Cyclic means that you have the longest carbons kind of connect at the end to form a ring. This right here is not a cyclic compound. This is acyclic. So you technically cannot have a cis or trans fat. But what you have here is a saturated fatty acid. So you probably have heard that saturated fatty acids are not good for you and that the unsaturated fatty acids are a lot better. Well, saturated fatty acids are not very good for you, and neither are trans fats. So what makes these similar to each other? Look at the way the molecule appears. So the shape of the molecule is such that the saturated fatty acid has a linear shape. And this is the same thing we see here with the trans fat. They both have a linear shape. Their overall arrangement of the molecule has a linear shape, right? So I hope you can see that in the way this pink box highlights around the molecule. But when you have the cis fat has more of a V shape. So it looks something like this, where my thumbs will be the double bond, and then you have the large groups aligned in the same orientation, or the opposite. It's hard to show that, but it will look like this. So with that double bond and the cis formation of those groups, it makes the cis fats have these V shape. And so when they're trying to pack, because fats are usually solid, so when it tries to pack, it doesn't pack very tightly. So if you look at this picture right here, it's difficult for cis fats to pack very tightly. And for that reason, cis fats tend to be a little bit more fluid and less dense. On the other hand, trans fats or saturated fatty acids can pack very well because the overall shape is so linear. As you can see here, it looks very linear, so it aligns itself very well and packs very densely. And when it does that, it forms solid fats in your body, and pretty much that's where we get plaque from, okay? So this is where that applies. And then moving on to our next type of isomer, we're looking at enantiomers. With the enantiomers here, to have an enantiomer, you have to have a chiral compound. A chiral compound normally has a carbon attached to 4 different groups. It doesn't always have to be a carbon, but it's normally a carbon attached to 4 different groups. So the carbon has to have 4 bonds. Carbon normally has 4 bonds. The carbon has to have 4 bonds, and there has to be 4 different groups attached on the end of that carbon. So right over here to your left, you have a carbon attached to 4 different groups. And you can see that. Now, when you have a chiral carbon, that carbon, when it's being made, its mirror image can also be made unintentionally. And so when I'm teaching this on campus, I usually like to say that it's like identical twins, you know, how they're formed. They almost look the same. When you see them, it's like when you see one and you see the other, they look almost identical, right? They look almost alike. And so with this case here, essentially, you have a molecule that when it's being synthesized, depending on the condition, its mirror image can be synthesized with it. It's very hard to tell this molecule and its mirror image apart. So when you're trying to think of a word to describe the molecule and its mirror image, the word that's used there is enantiomer. Enantiomer will be similar to the word twin or twins. When someone and their sibling were, you know how twins are made, right? Identical twins are made. You pretty much have one egg that gets fertilized and then it splits and then you have twins. That's the oversimplification. Okay, so my background is not in biology. I'm not strong in biology, but pretty much you have identical DNA in the twins because you had one egg and that egg was fertilized, and then that fertilized egg split, and that's how you have identical twins. So when you are referring to the twins, identical twins, you use that term identical twins, and people understand two different people who have pretty much the same DNA, close to the same DNA. Okay. Now, in this case here, you have two formulas that look exactly alike or almost exactly alike, but they are different. What makes them different? One is the mirror image of the other. And so when you have two molecules that look almost the same, but they're mirror images of each other, but they're non-superimposable, these molecules will be called enantiomers. So what makes them different? The fact that they're not superimposable. And so at this point, let me stop for a second. I'll be back. Okay, so I am back. I decided to grab my model kit here so I can show superimposable. So I have my carbon here and I'm building this so you guys can see what it looks like. I'm going to use 4 different groups so you can see these groups around the central atom. So of course, carbon is the central atom over here. I'm going to be using 4 different colors, and that way you can see. Oh, snap. Okay, I'm improvising, y'all. I was doing something else. I was trying to send stuff in before deadlines. I missed a couple of deadlines, so I'm trying to, improvise here. One's got to do what one's got to do. So here's my one molecules. Got all these colors. Now let me see if I can find the other molecule. Now to build the other molecule, I have to be strategic. And let me see if I can show you my desk. It's gonna be hard, okay? Guys, I'm improvising with this, so please bear with me if this is not very pretty. It's just, I'm trying to do the best I can. No, okay, let's go closer right there. To build this, I have to be very strategic and actually align the mirror image with the original image. Please tell me I have long bonds, enough of them. Wow, I have just enough to build the mirror image. Okay. So what I'm doing here, I'm not just, okay, so right there. So the mirror image, if it's red on the right, it has to be red here. So I'm gonna put a red molecule right there so you guys can see that. Oh, I'm sorry. You know what I realized? What happened in the last video? I realized that every time I looked away from the computer, my voice trailed off. It's really hard because I have to look away to grab stuff. Okay, right there. I'll try to keep my head facing the computer so I'm not fading off. It's so tough to do this. Okay, right there. So you see that? Now I get to put the yellow on the top. Maybe in the future I'll get a camera, right, for Christmas. The other issue will be how to use it, right? How do I set it up in my office? At home, I have my husband to help me. He's my IT guy. But okay, so I hope you can see this. Now I'm gonna pull this up since I'm done building my molecule. Right here. So we have the molecule on the right. This is the original, and this is the mirror image. Okay, so you can see that the mirror image is because the reds touch, the blues touch, and on either end I have the purple or maroon. It's hard to tell. Okay, now from a distance these look the same, right? You're like, wait, this is the same molecule. It's actually not the same molecule. Superimposable means that when you try to line these up, while the yellow lines up with the yellow, and the purple lines up with the purple. You see that? The purple and the purple line up. The yellow and yellow line up. Look at the red and the blue. They don't line up. Oh, I'm struggling. See? This is the part that makes them different. And so why do we want to recognize that these molecules are actually different from each other? Because when it comes to making molecules in the lab and synthesizing drugs and stuff like that in the lab, it's important to know which isomer you're getting. If your goal is to get the isomer on the right, but you get the isomer on the left, you have problems, okay? Because sometimes when it comes to the biological system in biochemistry, the molecule on the right will interact differently with your body than the molecule on the left. That's when you have a medication, especially painkillers or a lot of asthma medication, to tell you, well, this medication will help to dilate your bronchioles so that you can breathe better, but then here's all these horrible side effects, and then they write it in very small font, right? And then you have to read all that before you take the medication. That's because when they were making the good twin, the medication that heals you, the therapeutic compound, they unintentionally made the evil twin. So now when you're taking it, you take the good twin and the evil twin at the same time. Now, you may have a question, well, why not separate them? Unlike the other isomers where the physical and chemical properties tend to be different, I would say significantly different, with these molecules here, everything about them is alike. The molecular weight is alike, the melting point is alike, the boiling point is alike. A lot of things are alike, except for the way they rotate alike. So when you dissolve this compound, if you have a mixture of this compound and you dissolve it in a solvent and you test it, you pass light through it, you will know you have both compounds in equal amount. If a specialized, it's actually a device called a polarimeter. If the light that's passing through passes through undeflected. If you have more of one compound will rotate that light. It will bend the light one way. The other compound will bend the light the opposite way. So you will know you have one compound based on how they bend light. So I'm getting into the majors section right now. You guys are in non-majors class, so I will move on. But so here you're asked to draw 5 structural isomers for hexane. Remember, in structural isomers, which is also constitutional isomers, what you want to do here is just start off with the easiest one where the carbons are in series. The longest chain has got 6 carbons, right? And then you're filling the hydrogens around it. That will be your first one. Isomer number 2, maybe cut it down to 5 carbons in the longest chain, and then use one of the carbons, the 6th carbon, as a side chain. And that's pretty much how you work this out. I don't want to give you all the answers, but be creative. Think about it. The goal is for you to get different structures from the same starting elements, okay? And then with this one here, same thing. You have 3 carbons, 8 hydrogen, and 1 oxygen. The goal is for you to get 3 isomers. You can do that. Remember that cis and trans isomers only exist in a compound that has a double bond. So for that reason, you should be able to do cis and trans. You have to have a double bond in there. I see. For that, okay, you know what? I just realized something. This should be octene, because double bond compounds have their names end with ENE because they're in the alkene family. Right, so 3A should be cis-2 octene, not cis-2 octane, okay? So I made that correction right there. Same thing with this. When you have, when they're showing you, they're pretty much having you draw cis and trans isomers. Remember, cis is the hydrogen on the same side, and then trans, hydrogen on the opposite side. Because of that, for cis, the large groups will be on the same side, and then trans, they'll be on opposite side, okay? And that's true of all cis and trans. Okay, let's see. Oh, so over here in 4A, so I'm going to comprehensively go over this because the person who had the question never got a chance to actually call in and ask. On this one here, on 4A, B, and the rest of these, you're being asked to list the following as constitutional isomers. Remember, constitutional isomer would be like a structural isomer. or stereoisomers, or completely different molecule. Okay, so before you decide whether it's constitutional or stereoisomer, you have to find out if it's a different molecule. It would be a different molecule if the formula, the basic formula, the molecular formula is different. So just to help you with the first one here, look at the one on the left, the molecule on the left, and let's count number of carbons. So I need to keep track while I'm counting. It makes me focus a little more. On the one on the formula on the left, we have 2 carbons. So right here, C2, 2 carbons. Oh, by the way, when you're writing out molecular formulas of an organic compound, the convention is carbon first, hydrogen next, and then oxygen. If you have nitrogen, that comes next. Like Sean, carbon, hydrogen, oxygen, nitrogen. Okay, so we have 2 carbons. We have how many hydrogens? Ooh, 6 hydrogens, right? 5 here, the 6th one here. So C2H6. And then we have 1 oxygen on the left. On the right, we have, again, 2 carbons, so C2. We have 6 hydrogens, H6, and 1 oxygen. Since they both have the same molecular formula, then there is a chance they're isomers, right? If they don't have the same molecular formula, they're different compounds. Okay, the one on the left has got the carbons back to back and the oxygen on the right of the carbon. So our central atoms, hydrogen is never the central atom. Remember that from drawing Lewis structures. So the central atom is carbon, carbon, oxygen. So that will be CCO. That's the order of a central atom. On the right, we have COC. So obviously we have the same molecular formula, but the way the atoms are connected are different. So much so that we're getting different functional groups. But bottom line, they asked you a simple question. I'm over explaining. So for A, because the formula is the same, but the connection is different, we have a constitutional isomer. I will help you with 4B too, and then we'll move on from there. You guys can figure out the rest. Okay, so with 4B, oh, you know what? She did ask something about the structure, so skip that. I'm gonna skip 4B and do 4C, the one with the cyclic compounds. So with these cyclic compounds, please realize that these triangles actually refer to carbons in a ring structure. So remember that the corner, this is the skeletal structure right here, and you have 2 side groups. The corner of all of these triangles represent a carbon. So you have a carbon here, a carbon there, and a carbon there. And let's see, so the carbons are in there, right? You have 3 carbons. And then remember that each carbon is surrounded by how many hydrogens? Well, each carbon is surrounded by 4 bonds. So on this carbon alone here, we already have 2 bonds, and we're missing 2 bonds, okay? So the 2 bonds that I'm missing here are actually implied, but they're not shown because this is a skeletal structure. Ergo, the skeleton. When you have a skeleton, the flesh is missing, right? But you know that in the full structure, the flesh is there. So I guess the flesh that's missing here is a bond and a hydrogen. So from this carbon, there's 2 hydrogen bonds, well, not hydrogen bonds, 2 hydrogens that are bonded to this carbon that I'm missing, okay? So they're right here and right here. So I'm gonna count the carbons first. 1, 2, 3, 4, 5. So we have, for 4C, we have 5 carbons, right? Each corner counts as a carbon, and each end of a line counts as a carbon if the atom there is a carbon. Okay, so 1, 2, 3, 4, 5, 5 carbons. With the hydrogens, you can see you have 6 hydrogens here, 6 hydrogens here. And then you have 2 that are missing here to give this carbon 4 bonds, and 2 that are missing here to give this carbon 4 bonds. So we have 8 hydrogens, right? So C5H8. And then on this one on the right, same idea. On the corner, on each corner, we have carbons, right? Each corner represents a carbon. And then remember, what is missing on the corner is pretty much the number of hydrogens required to make each carbon be surrounded by 4 bonds. So let me count the carbons first so I don't get lost in all the details. I have 1, 2, 3, 4, 5 carbons. Okay? So C5, once again, is 1, 2, 3, 4, 5. And then the number of hydrogens. So I have 1, 2 here because these two are missing, right? Because we have 2 lines here, so we're missing 2 lines. That means we have 2 hydrogens here, 2 hydrogens, 3, 4, 5. There's a 4th hydrogen missing here because you have 3 already. So 1, 2, 3, 4, 5, and then 6, 7, and 8, 9, 10. Oh, okay. So just to make sure, remember that the carbon has to be surrounded by 4 bonds. So since this carbon has 2, it's missing 2. This carbon has 2, is missing 2. This carbon has 3, is missing 1. This carbon has 2, is missing 2. And this carbon, well, this carbon is satisfied. So we got 2 here, 3, 4, 5, 6, 7, and then 8, 9, 10. C5H10. Okay, I'll let you guys figure out the rest of them. Okay, I'm hoping that's what she was asking me about. So, oh, I guess I forgot to answer the question, right? I got a little excited there. Okay, since the molecular formula are pretty much different, right? On the left, we have C5H8. On the right, we have C5H10. The molecular formula is different. There's no way this would be an isomer. For molecules to be isomers of each other, the molecular formula has to be the same. Okay, so moving on to this one here. Let's see, they want you to label the cis and the trans double bond in the following. Remember, the double bond of the cis and the trans has to be around carbon-carbon double bond. That means these don't count. It has to be a carbon-carbon double bond. So do not count these as cis or trans. I'll give you one example only. Look at this one right here. These, on the end of these, are pretty much a carbon here and a carbon here. So for that reason, do you see the hydrogens? They're on the same side. So when I was learning this in high school, my teacher was trying to help make us learn this stuff. I was young then. I was like, I don't know what you're talking about. Cis, trans, all this stuff. And he would do this, cis, same. And I'm like, okay. I have not forgotten that. Cis, same. Trans, different. Cis, trans, right? So yes, I am making myself look ridiculous like he did, but I never forgot it. Cis, same side. So when the hydrogen on the same side, that makes it cis. So that you pretty much circle this one here as cis. Okay, I'll let you figure out the rest of them. And let's see, IUPAC nomenclature when it comes to the naming. So how much do you have? Oh, that's close to the end. So I'll help you with one thing. Should I help you with one thing? I'll help you with this complex one. C, with the IUPAC nomenclature. When you are naming functional groups, or you're naming groups, period, make sure that in this case, you are labeling the longest group, the longest continuous carbon chain. So when they say continuous carbon chain, that means you have a carbon and a carbon and a carbon, carbons and carbons back to back. So you want to track or trace these carbons back to back and get the longest possible combination. So I'm going to start from the left. 1, 2, 3, 4, 5, 6, 7. That's the combination that gives me 7 carbons back to back. And I'll try a branch direction. 1, 2, 3, 4, 5, 6, 7. That's another possibility. And I'll try another branch direction. 1, 2, 3, 4, 5, 6, 7, 8. Oh, we have a winner. The one going up is a lot longer than the ones that were going this way and the one going down. Okay, so when you're actually trying to label this and name this, you will label the one going up as your longest chain. So that will be the one starting from the left. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so first thing you want to do is identify your longest continuous carbon chain. The next thing you want to do is you want to know how to number that longest chain. In numbering the longest chain, please realize that when you have a double bond or triple bond or a heteroatom, it controls where you start numbering your longest chain from. What I mean by that is, if you look at your longest chain here, your triple bond, let me see, hold on a second. To get to your triple bond, you count from the carbons, right? So carbon 1, 2, 3. Triple bond is attached to carbon 3. Let me try to get to the triple bond from the right, top right, right? Okay, so up here, 1, 2, 3, 4, 5. So after carbon 5, or yeah, you get to the triple bond at carbon 5. Since I get to the triple bond sooner from the left, carbon 3, you will start numbering your carbon on the left. You number this as carbon 1, carbon 2. I hope you can see the mouse movements. I just thought about that. Okay, I'm not going to overthink this. Carbon 1 to the left, carbon 2. Then the third one has got your triple bond. So 1, 2, 3, 4, 5, 6, 7, 8. That's how you number it. And then you have to give the name based on the number of carbons. Okay. I'm seeing some issues here with giving you guys this. This question here was actually in the chapter. So they want you to know how to name this in chapter 10. Okay. Oh, no, is it 10 or 11? Okay, one of the chapters. Anyway, so when you have a triple bond, when you're naming compounds that have triple bonds using the systematic name, that's a very organized, ordered name that has a lot of rules versus the common name or the commercial name. Triple bonds end with Y and E, okay? So triple bonds are of the alkyne family, ALKYNE. So their names tend to end with Y and E. Since this compound has 1, 2, 3, 4, 5, 6, 7, 8 carbons, with 8 carbons, you use the prefix oct, okay? Since you have 8 carbons with the functional group that's an alkyne, you will write it as octyne. OCT for the 8 carbons, YNE for the triple bond. I'm not done. What carbon is the triple bond attached to? Well, we just counted earlier. The triple bond is attached to carbon 1, 2, 3. So that has to be stated somewhere. When you're going over this in your homework, you realize there are 2 ways of representing this. Sometimes it's written as 3-octyne. Since I'm not really teaching the nomenclature rules, I'm just helping you guys work through this. Please realize when you're naming compounds using a systematic format, between a letter and a number, there has to be a dash. Between a number and a number, there has to be a comma. Between a letter and a letter, there is nothing. Okay? So number, comma, number, letter, dash. Whether you're going from number to letter or letter to number. These are the small rules that chemists come up with, okay? So that molecule, the longest chain can be 3-octyne, but I have seen some books that write it as oct-3-YNE. So I'm going to spell this out. OCT-3-YNE. That's the other way of writing it. So you can write it as 3-OCTYNE or OCT-3-YNE. Okay, that's just the longest chain. Now you have to name the side groups attached to this longest chain because we're not done, right? So we said this top part was the longest chain. So these side groups have not been named. Remember, side groups are named. The side groups are all under the family, the alkyl group, ALKYL. And so when you name them, they tend to end with YL, and that's how you know the side group. So when the side group has 1 carbon, the prefix you use there is mes. So each of these side groups will be called methyl. I'm sorry if my voice is coming in and out. It's really hard. I'm trying to write. Okay, so methyl. But we have 2 methyls, right? And both methyls are attached to carbon number 6, right? 1, 2, 3, 4, 5, 6. So when you're writing this out, you have the first side group called the methyl attached to carbon number 6. So that will be named 6-methyl. 6 telling you where this side group is located. The other side group is also attached to carbon number 6. So 6-methyl. So we have on carbon number 6, 2 methyl groups. So when you're actually writing the final name, you consolidate the side groups. And it ends up being Okay, bear with me. 6, comma, 6, dash, dimethyl, and then dash, 3 dash octine. I'm gonna say it again. Actually, you know what? Oh, let me write it on the side so I can show it to you. 6, comma, 6 dash dimethyl. So I actually, when I was taking organic chemistry, I really liked the nomenclature part because to me it was almost like charades. It felt like charades to me because the name is very systematic and it's very ordered, it's very purposeful to let you know what the structure is. So theoretically, you name the structure of the molecule in such a way that you can get the structure from the name. Sorry, I'm trying to multitask here. Okay, let me show you the structure of the name I have right here. So you can see is 6, comma 6 dash dimethyl dash 3 octine. So what is this communicating? This is communicating that your longest chain is an octine. It has 8 carbons, and Y and E means there's a triple bond on the 3rd carbon. So you have a molecular structure, you have a structure of a formula that has 8 carbons on the longest chain. But you also have a triple bond from the Y and E on carbon number 3. From this longest chain, you have 2 side groups. How do you know? The number of the numbers right here. On carbon 6 and again on carbon 6, there are 2 side groups, and these side groups are called methyl side groups. So the idea is from the name of the molecule, you should be able to get the structure. Okay, guys, I'm going to end here before I talk too much. My voice is already hoarse from talking too much this week. So I hope you guys have a nice weekend, and please work on the lab and turn it in because it's worth points. If you have any more questions, let me know. Okay, thank you very much. And Crystal, thank you for hanging in there. I hope everything is going okay at work. I will talk to you all later. Have a nice weekend. Thank you. Bye. Okay, so this should mark the end of the meeting. So I hope you can hear me, Crystal, but I'm about to sign off. It is 5 o'clock. I'm trying to see if I have a lot of other things to get done, but I hope you have a nice weekend and that you are able to get to your lab. Okay, thank you very much. Bye. Did this end? Oh.